following is an introduction to analytical methods for the detection of the organic chemical pollutant polycyclic aromatic hydrocarbons. These pollutants, also known as PAHs, are nasty chemicals found in the atmosphere and environment. They are created by the incomplete burning of hydrocarbons such as coal, oil, gasoline, trash, tobacco, and wood. New studies have shown that foods can be a source of PAHs, such as charbroiled meats, barbecue foods, and even burnt toast. Humans are exposed to PAHs in multiple ways, including secondhand smoke, car pollution, and fuels in cooking. Burning solid fuels is the main source of PAHs in the atmosphere. Due to the small structure, 2 and 3 ring PAHs are easily dispersed by air or water. PAHs are naturally occurring. They are even found in the outer reaches of space. They have been thought to be linked to the early development of organic life. Natural production of PAHs include volcanic activity and bushfires. They can also be found in asphalt and roads, coal tar and pitch, as well as in many fungicides and insecticides. They are organic compounds composed of aromatic rings. They are neutral, non-polar molecules which have been identified as carcinogens in some, if not most, cases. Currently linked to skin, lung, bladder, liver, and stomach cancers, PAHs are a high-risk chemical that is important to monitor. HPLC is a fast and effective way to accurately analyze the levels of PAHs in liquids. As such, we have been using HPLC to monitor these pollutants in our environment. So what is HPLC? HPLC stands for high pressure or performance, depending on where you were taught, liquid chromatography. It is a highly accurate and sensitive method to analyze components of a liquid with a fast turnaround time. Using a mobile and stationary phase, analytes are separated due to the affinity to the stationary phase when pushed through a column by a mobile phase. A stationary phase is a solid coating or packing in a column that attracts certain analytes due to the chemical structure or reactivity based on the polarity and size of the components. There are 2 types of HPLC analysis referred to as normal phase and reverse phase. Reverse phase uses a polar mobile phase and a hydrophobic stationary phase. Hydrophobic molecules will absorb into the stationary phase, and any hydrophilic molecules will elute from the column first. In normal phase, the stationary phase is polar and the mobile phase is nonpolar. The stationary phase's particle size also varies when determining the best suited for analysis to allow for varied sized molecules to be excluded. So the solution is passed through a column packed or lined with a stationary phase appropriate for the analysis, and the mobile phase carries the analyte through. The different components pass through at different times depending on their affinity to the stationary phase. Detectors are used to identify and quantify the unknown components. There are many different detectors available for the HPLC analysis, including but not limited to UV, diode array, thermal conductivity, fluorescence, electron capture, photoionization, and flame ionization. The benefits of HPLC are: HPLC is highly accurate and incredibly fast. The stationary phases are reusable, but over time they will degrade, and this will be noticeable in the results. It is reasonably easy to use, but one could spend most of their life mastering it. With the ability to change the column, mobile phase, and its concentrations, for example using an isocratic concentration or a gradient concentration depending on the analyte, and changing the detector to suit the analyte and the mobile phase, HPLC has a wide range of very diverse analytical abilities. That being said, this machine is not for any Joe Schmo who can test a sample's pH. No, HPLC is a finely tuned analytical dynamo that needs the time and patience of a skilled lab technician. Although easy to use, this machine needs constant upkeep, and the components can be highly expensive, so care and caution must be taken when dealing with any HPLC apparatus. A problem with PAH detection is the inherent possibility of low, and I mean really low, concentrations. This results in the need for ultra-sensitive apparatus to be able to detect it. However, with great sensitivity comes great cost. So with modern innovations in luminescence, some novel ways to overcome this have come to light. Luminescence is the release of light by a substance that is not caused by heat. Luminescence can be observed in chemical reactions, electrical energy, and subatomic motion. There are 3 main types of luminescence, being fluorescence, phosphorescence, and chemiluminescence. Luminescence relies on a detector to quantify the emission of light from the sample. For the sample being analyzed to be quantified, it must be in a state easily detectable. For this, it is common for an analyte to be immobilized to a suitable support solid. This gives rise to 2 main types of analysis: solid phase luminescence, SPL, and support matrix luminescence, SML. Light emission comes from either the analyte itself or by an immobilized indicator interacting with the analyte. Solid phase probes are very useful when paired with a flow system like HPLC. Using solid phase probes as a detector for HPLC increases the accuracy and specificity of the analysis. The benefits of solid phase luminescence are again the speed and sensitivity of detection. The solid phase can be reused many times, and batch methodology can be implemented to determine large numbers of samples. Due to the sensitivity of the analysis, there comes a need for specific probes and conditions for each analyte in question. This increases cost, time, and expertise needed to produce an accurate and sustainable result. In conclusion, PAHs are an extremely important family of compounds to monitor. With HPLC and novel detectors such as solid phase luminescence, we are at the cutting edge of identifying and therefore reducing the pollutants in our environment.